Hi, welcome to the AP Physics 1 playlist for circular motion and centripetal force. This is a unit that you did last year, just like kinematics and forces. There will be a few new things, but a lot of this will just be reviewed. There will be a few new things though, and some harder questions. So last year we started off with the basic question. We have objects, we have certain situations where objects move in circles. Why is that? Why do these objects move in circles? And it happens because some force being constantly directed perpendicular to the velocity. Force is constantly directed perpendicular to the velocity. So let me show you what I mean. Here's an object. Let's say it has initial velocity to the left, but it's experiencing a force downward like this. Now these are two competing influences on that object. If we didn't have this downward force, the object would just move to the left. If we didn't have this leftward velocity, the object would start from rest, but it would gradually accelerate down, and its velocity would end up being down. So in a situation like this, which way will the object move? Well, initially, because it doesn't have any velocity initially downward, it's going to move primarily to the left. But because of that force, it is going to start to accelerate in that direction and gain velocity in that direction. So what ends up happening is the object starts to move to the left, but it also starts to move down a little bit. And it follows a path sort of like this. Here's the initial position of the object. It follows a path that's somewhat left, but also starts to go down a little bit till it gets to, let's say, like right here. You know, you look at it like a second later maybe. At this point, the object is still moving to the left, but it's also moving down a little bit. So the velocity is like this. Okay, there's the velocity vector. Now, in order for it to be circular motion, the force can no longer be simply down. It has to be still perpendicular to the velocity, like this. Okay? Now, what would that cause? Well, the initial velocity right now is in this direction. Okay? So the object's going to primarily move in this direction, but the force is going to cause some acceleration in this kind of down into the right direction. So what we're going to get, here is the initial, here is the second position. We're initially going to get motion along that velocity vector. We're also going to get an acceleration a little bit down and to the right, which is going to cancel out that leftward velocity. Now we're down here, and we have the velocity downwards. And if it's circular motion, that means that the force has now rotated and is now to the right. So looking at an entire kind of motion map of this, we would have something doing the following. Here's where it starts. Object gets down to there. Here. Here. And so we have this entire pattern as it goes around an entire circle. And the neat thing is, the reason that this motion ever even happens in the first place is because the force is always directed inward toward the center of the circle. Okay, and if you notice all of these points, the force is always inwards towards the center of that circle. And we have a name for when a force acts like this. It's called the centripetal force. The symbol is Fc. Whenever you see the little c as a subscript there, that means centripetal. Okay? Now, what the centripetal force is, one thing I do want you to realize, look how there are the letters, kind of in order, N, E, T, that appear in centripetal. By the way, it's not centrifugal, it's centripetal. They're two different things. See the letters N, E, T there, and remember that the centripetal force is just a very fancy name for the net force directed inward toward a circle's center. And this is the force that ultimately causes circular motion. Okay? One thing I do want to point out, since we're talking about a net force here, the centripetal force is not a new force. Okay? It's not something new that you're learning about. It's not a new type of force. It is simply another word for the net force when we're dealing with circular motion. Okay? So it's not a new force. Matter of fact, the centripetal force, as we'll see in these examples, is caused by forces that you already know about. So other forces act as the centripetal force. Okay? So it's not a new force by itself. It shouldn't go on any free body diagrams. Just like a net force doesn't go on any free body diagrams because it's not a force in and of itself. Centripetal force does not go on any free body diagrams. It's not a force in and of itself. Some other force acts as the centripetal force. And my last point that I want to make is that the centripetal force, just like a net force, you can have one force act as the net force, you can have a combination of forces act as the net force. The same is true for the centripetal force. Could be one or more forces acting in or out of circle. And that's something that's a little bit new this year. We're going to deal with situations where we have more than one force making up the centripetal force. So I just said when we draw free body diagrams, you're not ever going to put FC on the diagram itself. So how do we set up our free body diagrams? I learned this trick in college. When you're drawing free body diagrams for objects in circular motion, one of the keys is to make the direction toward the circle's center. Usually we label them as X and Y. We're talking about the axis here. Usually label it as positive X, positive Y. We're not going to do that here. Or, well, you could do it, but the direction towards the center of the circle should be labeled positive C. And what this does is it helps us to line up the forces to see which contribute towards that circular motion. So in other words, which forces are pointing in towards the center of the circle and causing that circular motion, which forces do not do that, or which forces point out away from the circle. Those still affect circular motion, but something that's perpendicular to the direction towards the center of the circle, that has no influence on the circular motion. Those forces exist, they just don't do anything with the motion. Okay, so it helps to line up forces to see which contribute to circular motion. We're going to have 4 examples here. Our first example is going to be a washer, just like a little silver metallic washer, that is swung in a horizontal circle on a string. Okay, so here is our little drawing of it. Again, we're going to have 4 examples, so you want to space this out well on your page. Here's the path that the washer makes. Here's where it starts off. So we've got something that looks a little bit like this. It eventually moves, up to here. Okay, and it's just moving around this circle. So at this point, the washer is moving, let's say, up, moving to the left up here. So it's moving counterclockwise around the circle. Now, if you're trying to analyze this, what you're going to do is you're going to say, okay, I need a free body diagram. So I'm going to draw a free body diagram, label my washer, and let's draw a free body diagram for this point in the washer's motion right here when it's on the right side of the circle. Okay? If it's on the right side, what direction is the center of the circle in? That would be to the left. So I'm just going to write plus C. By the way, let's just say right now this is a top view. Okay, you're looking down on it. Obviously, there's a force of gravity acting down on the washer, but in a top view, you wouldn't be able to see that. So we're just going to deal with whatever force is causing it to point in toward whatever force points in towards the center of the circle. That would be the tension. It's on a string. The string is making it move around. So we say that the centripetal force, the net force in towards the center of the circle, is equal to the tension in that string. Okay, it's as easy as that. So in this case, the centripetal force is given by the tension. Centripetal force equals tension. Another example of a free body diagram with circular motion would be the following. It would be Earth's orbit around the sun. Now I'm going to draw a diagram that is wildly not to scale. So we've got, okay, here's Earth. It's going around the sun. Here's the sun. What would a free body diagram of Earth at that point in its motion look like? Well, we know that there's a force of gravity inward on the Earth like that, so our free body diagram might look like this. Here's the Earth. The direction towards the center of the circle is to the right this time, so we're going to label to the right our positive c direction. And the force of gravity is the force that points in that direction. There's no other forces on the Earth. So, in this case, we would say that the centripetal force is equal to the force of gravity. We wouldn't say it's equal to the tension this time because there's no string that is connected to the Earth. So, this case, you see that there's a different force acting as our centripetal force. We've got a couple more examples. This one is an interesting one. A car going around a curve. So we've got a road surface. I'm going to draw kind of a weird little road surface here. All right, there's our road. Here's our dotted line. Make sure we don't cross it. Okay, there we go. And let's say that we have a car that's right here. Okay, this is our car. And we know that the car is going, let's say, counterclockwise around our loop here. Well, so what I'm going to do for this, because this is tough for a lot of people to see, is I'm going to draw, here's the behind view of the car. This is top view, as if you're a bird watching this. Here's the behind view. Behind car view. Okay, so there's a wheel, there's another wheel. Okay. Here's your windshield. Okay. So we know that the car is going into the page. Here's the ground. Okay? So the car is going into the page. What sort of forces would act on this car? Well, an obvious one would be gravity. That would point straight down. Another one, and I'm going to run out of room here, would be the normal force, the force upward from the surface. And if the car is going to turn, neither of those forces, as you can see, are pointing in towards the center of the circle. The car is going into the page. That means the car is driving like down through my page right here. It's not coming up out of the page, it's going down into the page. So, we're missing a force here because there's no force that points in towards the center of the circle. So, the question is, what if you think about the forces that are acting upon the car, what force would allow the car to turn? Or what force, if we removed it, would cause the car not to turn? Think about the force of friction in this case. If we remove the force of friction from this car, imagine that you just put ice all over the road surface, is the car going to be able to turn? No, the car is going to slide straight through the turn. So in that sense, it's almost as if the car is moving left to right across this road. It's starting on kind of like the left edge of the road, and if it can't turn, it'll eventually come to the right edge. That's what happens if there is no friction. If there is friction, then the car can make its way around the curve. What that means is that friction must point in towards the center of the circle, like this. So if I were to draw a free body diagram of the car, I would put down the normal force, the force of gravity. Oh, I need my axis. From the car's position right here in towards the center of the circle to the left, I'm going to call that C, but there are other forces. So I'm going to label this as still the positive Y direction. Okay, I can mix C and Y or C and X or whatever I want to. It's just that C should really be the direction towards the center of the circle. It's a nice little trick. Helps you realize which forces are contribute to the centripetal force. So, to the left is my force of friction. Now, which of these forces contribute to the actual turning motion? All we have to do is look at which forces are aligned with the direction of C. That's just the force of friction. Fn and Fg are there, but they're completely in the positive or negative Y direction. So all we're dealing with is the force of friction pointing in towards the center. So, in this case, the centripetal force is equal to the force of friction. Okay. Last example, before we go on to the back, is an object that gets swung in a vertical circle. Okay, let's see. Okay, you guys should be able to see all this right now. So what I'm talking about, earlier we did something swung in a horizontal circle. Now we're going to do something swung in a vertical circle. And there's two spots that I want to particularly pay attention to. So you can imagine it's a washer swung in a vertical circle this time. I want to pay attention specifically to the very top and the very bottom. and the object is moving again, just for the sake of easiness, counterclockwise. When that object is at the top, what are the forces that act on that object? Well, first of all, we need an axis. The axis here, I suppose, at the very top, towards the, we need the C direction towards the center of the circle. That would be like this, plus C. At the top, there's a string pulling the object down, so we have tension. But there's also a force of gravity, and that also pulls the object down. That doesn't ever change. So I have two forces pointing down, T and Fg. If I want to talk about the centripetal force in this case, I would write that the centripetal force is T plus Fg, tension plus the force of gravity. On the other hand, if I want to talk about the object when it's at the bottom, which one of those forces is different? Well, at the bottom, gravity still points down, but the tension is now up. Which way should C be? Well, C, let's see, towards the center of the circle, that would be up. So my forces would be tension going up, force of gravity going down, and my centripetal force would be tension in the positive C direction minus the force of gravity in the negative C direction. So you can see the location of the object depends or can change what the net force or the centripetal force looks like. So that's kind of interesting. So what you've seen so far is that we have different forces that act as a centripetal force, and you've also seen that there could be one or more forces which contribute to circular motion. The centripetal force, always points in towards the center, and it doesn't have to be just one force. It was in these cases, but it could also be a combination of forces. When I come back, we're going to talk a little bit more about some circular motion topics before we get into some examples.